Hello, I'm Tina. This talk is going to be about a paper, Quantum Free Games, which is joint work with Anand Natarajan at MIT. So the main topic of this paper is quantum free games, and the main objective of the work is to work towards a tighter understanding of quantum generalizations of classical free games. So to tell you what free games are, I have to first tell you what a multi-prover game is. And in the multi-prover game setting, we generally have a single verifier called Arthur conventionally, which is PPT bounded. And Arthur interacts with two all-powerful provers called melon1 and melon2. And the model is as follows. Arthur sends questions x and y to melon1 and melon2, who are not allowed to communicate after they receive Arthur's questions. And then melon1 and melon2 send back answers A and B. And then Arthur does some computation to decide whether or not to accept the melons in this game. You could also have more provers and more rounds, but this definition will suffice for us. So in normal multi-prover games, or multi-prover interactive proofs, MIPs, the questions that Arthur sends, x and y, are allowed to be correlated. So how would this be a useful property? Well, we could look at one example of how this could be used. So let's suppose that there's some instance of a graph that Arthur wants to know whether it's colorable or not. And the melons, of course, know whether it's colorable or not because they are all powerful. So what could Arthur do to find out? Well, Arthur could do the following. He could ask melon 1 for the colors at the endpoints of a randomly chosen edge from the graph. And he could ask melon 2 for the color of one vertex on that edge. And then melon 1 and melon 2 respond. So then the check that Arthur does is he checks that melon 1's two colors are different and that melon 2's color is consistent with melon 1's answer. So note that because the melons can't communicate after they receive Arthur's questions, the only way they can be consistent with each other in this test is if they previously agreed to answer according to some fixed assignment. And the reason is, if melon 1's answers depend on the edge that he was given, which is the only way he can cheat, if the graph is not actually colorable, then melon 2 won't be consistent with him, because melon 2 doesn't know what edge melon 1 got, since he is not allowed to communicate with melon 1. So in this way, note that Arthur can verify even exponentially large coloring instances. So it only takes O of log n bits to write down the name of an edge or a vertex, where n is roughly the size of this instance, for example, the size of the adjacency matrix of this graph. So that is basically the multi-prover game model. Of course, it's very important in classical complexity theory. MIP2 is equal to next is one of the most important results, and the techniques in that proof eventually led to the proof of the PCP theorem. So now let's talk about free games. So the model is the same with a one difference, which is that in a free game, the questions that Arthur sends to melon 1 and melon 2 are not allowed to be correlated. So note that with this constraint in mind, we can't verify exponentially large coloring instances using the consistency test anymore. And the reason is, so this protocol relied on sending an edge and then a vertex that was correlated with the edge, right? It had to be one of the vertices that was on the edge. So if you aren't allowed to do that, the best you can do is sort of send a bunch of random edges, a bunch of random vertices, and hope for collisions. So you hope that one of the vertices will just happen to lie on one of the edges. Now this is fine when the graph is small, but when the graph is large, this gets quite bad. So we expect to send about root n vertices or edges before we get a collision, where n is the number of vertices or edges in the graph. So we'll assume in this talk that the number of edges is always approximately O of the number of vertices. That tends to be for free coloring and most other problems where the hard instances are. So since the work Arthur does, in order to send his question scales as root n instead of as log n, we can only hope to verify polynomially large instances using this method. So this intuition was formalized by Aronson, Impagliazzo, and Moshkowitz in 2014, who proved that AMK is equal to AM for any polynomial k. So this notation just means the free game version of MIP with k provers. So AM, as we know, is equal to NP under plausible assumptions. So under plausible assumptions, introducing the freeness constraint results in an exponential decrease in deciding power from next to NP. But there is something you can do with a classical free game that you couldn't do in any one-prover verification model. And that is using only about root n bits of communication with the two melons, Arthur can verify, let's say, through coloring, an NP complete problem. So the protocol is actually exactly what we described. Arthur simply sends random edges to melon 1 and random vertices to melon 2 and hopes for collisions. And we already reasoned that it will take about root n edges / vertices before Arthur gets collisions. And so it will take roughly root n bits to communicate these edges or vertices, maybe really like root n log n. And so Arthur could decide through coloring using only root n bits of communication with his two melons. Where by decide, we mean decide whether the instance is satisfiable or far from satisfiable. We'll just pretend that's always the case here. We have the classical PCP theorem to help us do that. So if there were a one-prover proof system which allowed Arthur to do this, then he could solve through coloring in a sub-exponential time, just by brute force searching over all possible melon answers and seeing which ones he would accept. And we don't believe that it's possible that it's to solve through coloring in such a short time. That's called the exponential time hypothesis. So it's unlikely that such an efficient proof system would exist when there's only one melon. And note that when there are two melons, the brute force search problem becomes more complicated because now you have to factor in the constraint on the two melons that they can't communicate. There's always some answer in the two-prover setting that Arthur accepts, regardless of whether the instance is satisfiable or not. So finding an accepting response is not enough in that case. Okay, so now I've told you what free games are, and we want to look at quantum generalizations of free games, and it's not exactly clear how you could generalize it quantumly. There are sort of two versions that we looked at. So the first one is QMA2. I'll talk a bit about that, and then I'll move on to another one called AM star 2. So Aronson, Impagliazzo, and Moshkowitz were actually inspired to work on AM2, the complexity class corresponding to classical free games, by a quantum class called QMA2. So QMA2 is the same as QMA, but with two quantum witnesses instead of one. So QMA is quantum NP. Instead of having a classical witness and a classical verifier, you have a quantum witness and a quantum verifier. Now, QMA2 is where you have two quantum witnesses, or you can imagine that Arthur gets given two witnesses by two non-communicating and unentangled melons. So this distinction would, of course, be silly in the classical case. What does it mean to have two classical witnesses? You could just join them together and then you'd have one classical witness. But it's not necessarily silly in the QMA setting. And the reason is, if you have this set up, you can guarantee that the two states that melon 1 and melon 2 give Arthur are unentangled. So if unentanglement were a property that Arthur could check for himself, then QMA2 would be equal to QMA. But we don't know how to check that efficiently, so it remains open whether QMA2 is equal to QMA or not. So the complexity of QMA2 is not super well understood. The best upper bound is next. The best lower bound is QMA. And maybe the most compelling concrete example of something which can be done in QMA2, but not in QMA, is verifying NP in sublinear communication. So it's not a coincidence that this is, an application for the class AM2 and also for QMA2. And to understand why they're so closely connected, we can look at how we would convert the AM2 protocol that we saw earlier for verifying 3 coloring in sublinear communication into a QMA2 protocol. So I lied, let's actually do it in a QMAK protocol where K is going to be roughly root n, where n is the instance size. So instead of 2 provers, we'll have a lot of provers. So let's recall how the AM2 protocol for 3 coloring works. So Arthur sends uniformly random edges to melon 1 and uniformly random vertices to melon 2 and hopes for collisions. Now, let's just establish notation. We'll use C of E as a shorthand for the colors assigned to the endpoints of edge E, and C of E as a shorthand for the color assigned to vertex B. Let's say Arthur sends K edges and K vertices. It doesn't have to be the same number K, but let's just say it is for simplicity. So to turn this into a QMA-K protocol, we need to turn each question response pair into a single quantum state. So remember in the QMA model, QMA-K model, you have one-way communication. The Merlins send states to Arthur, and Arthur doesn't get to say anything back. So let's say we have 2 K Merlins. Let's give ourselves a little leeway. And let's suppose we divide them into left Merlins and right Merlins. So we could have all the left Merlins send Arthur this state. So what is the state? It's a superposition where each item in the superposition is this pair of registers, the name of an edge, and some color assigned to that edge. And then it's a superposition with some weights. And it's a superposition over all the edges in the graph. And similarly, all the right Merlins could send Arthur this state, the vertex state, which is the same, but now we have the name of a vertex, color assigned to that vertex, and it's a superposition over all the vertices in the graph. So what's the point of this? The point is, if these weights, alpha E and alpha V, are the same, which would mean that they would be equal to this, then measuring these states in the standard basis is equivalent to asking a uniformly random question in this protocol and getting the answer. So it would be the same as if, this you should view as Arthur's question, and this you should view as Merlin's answer. It's just the Merlins are encoding all of their answers to Arthur's possible questions in this superposition state. So this protocol was described by Chen and Drucker in 2010, and they showed that this works. So you can verify 3 coloring using this protocol in QMAK in roughly root n log n bits of communication. So it's root n is K and then log n, because these states are not actually constantly sized, they're roughly log n sized. And then the number of provers is also square root n. So they develop a test called the uniformity test, which morally allows Arthur to certify that this property, that all of the edges are weighted equally, and the same with all of the vertices. So it would be bad if the Merlins could make these weights unequal, right? Because then they could just weight the parts of the graph that are actually colorable, even though the whole instance is not. So you do need something in this protocol to certify that indeed all of these weights are approximately equal. This is exactly what this uniformity test developed by Chen and Drucker does. Of course, but then everything in the protocol hinges on the uniformity test. So the limitations of your protocol are also the limitations of the uniformity test. In particular, the uniformity test requires short answers. In this case, it is the case because these colors, there are only 3 colors, so each one can be described in a constant number of bits. And also, the Chen-Drucker analysis of this test requires unentanglement between all the separate states, between all of the separate copies of this state and this state that are sent to Arthur in the protocol. So that's why there are so many provers, because you need the unentanglement guarantee between all of them. So, okay, that's a protocol which verifies 3 coloring in roughly root n bits of communication in QMA2, and we know from earlier that it's an analog of the protocol that verifies the same thing in the same amount of communication in AM2. So, you might wonder, is this root n necessary? Is it optimal? Could you get, n to the epsilon or even smaller, log n or something? So Brandau, Christandel, and Yard in 2010 showed some evidence that it is optimal. They find a way to convert any QMA2 protocol for verifying 3 coloring, where the verifier does not do any entangling measurements, into an algorithm for 3-sat taking approximately 2 to the communication squared time. So basically, if you could do better than root n amount of communication, you would be able to solve 3-sat in sub-exponential time, and we don't believe that's possible. Now, what do I mean by the verifier does not do any entangling measurements? The setup is as follows. You should imagine now that the verifier is also composed of 2 entities, one of which, Arthur, receives the state given by Melon 1, and the other one, called Lancelot, receives the state given by Melon 2. And then Arthur and Lancelot measure their states separately without communicating, and then they do some classical computation together in order to decide whether to accept or reject. So if you had a protocol of this form to decide 3 coloring that had less than root n bits of communication, then you would be breaking the exponential time hypothesis. I said this already. Now, you'd think that maybe Chandraka fits the bill, the protocol we just described for verifying 3 coloring in QMA2. QMA root n. That's really the problem. It has root n provers. And the BCY result only applies to QMA2 with 2 provers. So it was an open question to show whether BCY was tight. So there is a way to get it down to 2 provers. This is Harrow and Montanaro from 2010. But it requires entangling measurements. So again, that doesn't fit the bill here. It doesn't match the bound that was given by Brandau, Christandel, and Yard. So there's sort of an obvious thing to do when you have the Chandraka protocol with its many provers and you want it to be 2 provers. You could just batch the prover states together. So you can, all of the states which come from left melons, these states, you just make them come from 1 prover instead. And all of the states which come from right melons, these states, you make them come from the 2nd prover. So now you have 2 provers. Now, of course, the obstacle is the uniformity test analysis given by Chen and Drucker, which only works if all of the copies of the edge states and the vertex states are unentangled. But, that's an analysis. There's no reason a priori why it wouldn't work. So we kept trying to find counterexamples for this 2-prover protocol, and we failed. So then we tried to prove it was sound, and that actually worked. So basically, we reanalyzed the Chen-Drucker uniformity test to show that even without any unentanglement guarantee between the copies, it satisfies a form of soundness. So we can't guarantee anything as strong as what Chen and Drucker get, which is that the amplitudes are actually all approximately equal, because that only makes sense when the copies are unentangled, and we can't guarantee that. But we can guarantee that measuring the question registers in the standard basis approximately generates uniform randomness, and that's sort of exactly the property that we wanted to simulate. Over here, we wanted these weights to be equal precisely because then measuring the state in the standard basis would be equivalent to Arthur asking a uniformly random generated question and Merlin giving an answer. So this allows us to show that the Brandau-Christandel-Yard result is actually tight, up to log factors. And the bonus is that arguably our analysis is kind of nicer than the original Chen-Drucker analysis. At least it's shorter and maybe easier to digest if you know the ideas behind the proof. Okay, so for the last part of the talk, I'll switch tacks and talk about the other 2 results in the paper. I've chosen to focus on the first one, the QMA2 related one, because it's more accessible. Which ones are more interesting, I think, depends on your perspective. But in the last part of the talk, I'll briefly summarize the other results. So, we already talked about one quantum generalization of the classical free game, QMA2. There is another one, maybe more natural one, where you have the same model, as a normal free game. X and Y are not allowed to be correlated. And you have Arthur sending these X and Y to Melon 1 and Melon 2, and they give answers A and B. The only difference is that you allow Melon 1 and Melon 2 to share entanglement. So this transformation on a classical game to make it quantum should be familiar. That's exactly the transformation that takes MIP, classical multi-prover games, to MIP star, quantum entangled multi-prover games. So recent results have shown that MIP star 2 is equal to RE. Now, Aronson and Pagliazzo and Moshkowitz also showed that AM2, classical free games, are weaker than MIP2, classical multi-prover games, under plausible assumptions. So we might ask the natural question, is the same true of AM star 2 and MIP star 2, where this is quantum entangled free games, and this is quantum entangled multi-prover games? So in this paper, we show that the answer is actually no. In fact, AM star 2 and MIP star 2 are equal, and they're both equal to RE. So this means that free games are as powerful as general games in the entangled case, even though the freeness constraint led to that exponential decrease in deciding power in the classical case. So we show this by showing that MIP star 2 with constant-sized questions and polylog-sized answers is equal to general MIP star 2. So this result, MIP star 2 equals RE, had polynomial-sized questions and answers, and we show that, in fact, you can get away with having very short questions and pretty short answers. So then, if the questions are constantly sized, and getting collisions is very easy, which is why you can naturally generalize this to AM star 2 being equal to MIP star 2. So I'll remark that the previous fast lower bound on AM star K was Brandau and Harrow from 2013, which put NP in AM star with O of root n provers. So why are we able to do better? Well, because we can leverage the powerful tools developed by these authors of MIP star equals RE, which are based on self-testing. And the magic of self-testing is that it allows us to force the provers to introspect, which is terminology developed by these authors. And what it means is we can force the provers to generate their own questions, their own long questions when they play an entangled game. So this allows us to avoid having to send very large questions in order to achieve a constant probability of collisions, which is sort of the problem that we had. Why introducing the freeness constraint in the classical case decreased the power of the multi-prover game model. Now, there's another, once you know about this result, maybe there's another natural question, which is, can you do better? We showed that MIP star 2 with constant sized questions and polylog sized answers is equal to general MIP star 2. So, what is the smallest possible amount of communication in an MIP star protocol which is able to decide RE? For example, maybe can an MIP star 2 with constantly sized questions and log n sized answers decide RE? And we show that the answer is no. So using a link to Kolmogorov complexity, we show that any MIP star 2 protocol deciding RE must use at least O of log n bits of communication. So in more detail, we show that any MIP star protocol deciding RE in some smaller amount of communication than O of log n can be simulated by a deterministic Turing machine running in exponential time with some well-quantified amount of advice. Then we just prove a lower bound against exp to show that exp is not in exponential time with this amount of less than 2 to the n amount of advice, basically. And then the conclusion is that you can't have an MIP2 star protocol with too little communication, or you could convert it to a deterministic Turing machine that uses too little advice relative to this lower bound against exp. And exp is contained in RE, so the result holds for RE as well. So interestingly enough, this is not quite tight. Recall that we proved that MIP2 star with constantly sized questions and polylog-sized answers is equal to RE, and the lower bound is O of log n. So the difference is polylog versus log. And we think that the upper bound is the one that can be tightened. We think that if you can recover a quantum sound PCP for NP, then you could make it tight. And we think this is probably an object that exists, but constructing it seems to be a difficult problem and an interesting direction for future research. So that's basically all I have to say. Thank you.